And now, most of the time, you will see that when we talk about OS, we say that OS creates a layer because as a system software, it creates a layer between the operating system, that is the application software, and the hardware at the bottom. Right. But if you think in reality, a bunch of codes can't be working in that way. It's a concept that helps us to understand the roles and functionalities of the OS, the roles and responsibilities of an OS. It's a concept that we create, and we will, in these course, in almost every chapter, we will be talking about this concept. We will have to stick to this concept. But in essence, what is an OS? An OS is a bunch of codes which, just like any other software, must be loaded on RAM and will be running on RAM. And as it keeps running, that's it. It will perform different tasks. Now, these different tasks have been arranged and organized in such a way that it gives us a conceptual, that wonderful concept of having a layer of software right in between the application software and the hardware. And of course, as these codes will be running, some of these codes will will in fact control the interactions between other codes, that is other software, the application software, and the underlying hardware. So that is something that we'll talk about. Apart from that, we'll also talk about, if time permits, about some hardware components, basic ones. I think I mentioned RAM, then hard disk, then system bus, CPU. We already know all these things, but just a quick reminder because at the end of the day, these are the things that OS will be interacting with. Okay. We will also talk about that concept in all details and structure of OS. All right. So these are some of the topics that we're going to cover in this part that we called introduction. All right. So let's get started. As I said, if you have questions, you can ask me straight away by turning on your microphone. No problem. Computer hardware review and operating system concept. And this is the word that I was talking about, the concept. Because whenever, from now on, you will see wherever a person is trying to explain something about an OS, they always say that this is the application software, the apps are running in this layer, the hardware is in this layer, and that is where the OS is. This is an oversimplified concept. But we understand that OS is just like I mentioned, that OS is a bunch of codes. And these codes, just like any other software, must be on RAM, must be somewhere on the RAM. And they're running. Now, as they keep running, they perform certain tasks. And these tasks are to coordinate and control the interactions between some other codes, that is the apps. The apps are probably running in this part of the RAM, right? Because we know that any software that wants to run, any program that wants to run must be on RAM. And the underlying hardware. The hardware this is where OS is an important concept. Although we use the word underlying hardware, but that doesn't necessarily mean there is no concept of uh, upper layer and bottom layer. Try to understand. The hardware is the hardware, the interactions are interactions. So to control and coordinate all the interactions with, I write down these two words, control. Please remember, if anyone coordinate, anyone at any stage in a very casual asks you, what does an OS do? Simply use these two words, control and coordinate, interactions between apps and hardware. Now, how does it do that? I mean, how does it implement? Of course, a bunch of codes inside the operating system will do this controlling and coordination thing. But how do they actually do that? How do they actually implement it? The OS implements these things by switching the control. Now, this is a very interesting word because switching the control, we understand switching the control. So if you are more interested, if you say the teacher, what do you mean by control? Okay. Control is essentially the logic inside or embedded into your algorithm, isn't it? Think in a critical way, you'll understand what I mean. Essentially, a computer program is nothing but flow of logic. We call it in a casual way the flow of logic. Okay? The flow of logic. So as a flow of logic is basically what we call switching control. Now, switching control is a very interesting thing because the whole concept of switching control, if I can is this thing right here is switching control is, again, I go back to the concept, the old concept of OS right here. Your softwares are here and hardwares are here. So what do we mean by switching control? Switching control means this OS is sometimes serving the software. That means listening to the software. And at other times, it is interacting with the hardware. Again, it moves back to the earlier mode, talking to the software. I, I try to use a very simple words like talking and interacting. Okay. Now, that is what it does. It is talking to the software. And again, it switches the control, switches the mode of operation, and starts interacting with the hardware. So the codes inside the OS, inside your OS, are written in such a way that they can constantly switch from one mode to another mode. And these two modes are what we will get to know very soon. And we'll have to remember the rest of the course. It's called the user mode, or, well, user mode, sometimes called buffer, and the kernel, or supervisor mode. Supervisor mode. So clearly, OS, this is OS, this is OS. OS has a user mode and a kernel, the supervisor mode. So think about the software, the codes that I was talking about inside OS. So they have been organized and arranged in such a way that the flow of logic will constantly keep toggling from user mode to kernel mode to user mode back to kernel mode, back to user mode. If for any reason these logic or the control get stuck in one mode, the OS will become non-responsive. Naturally, if it is stuck for some reason for too long in the kernel mode, then the apps will suffer. The softwares and the apps are running right here, the user mode. The apps will suffer because no one is talking to them. No one is listening to their requests, whatever service requests they are asking for. Similarly, if OS is stuck with this user mode, then no one will be interacting, or rather passing the commands to the hardware and getting the feedback from them and handing over back to the apps. So no one will be paying attention to that. So if in OS, for any reason, and there can be several reasons, and I mean many reasons, because of which this situation can arise. If it happens, then your OS will become non-responsive. And from our own experience, we know sometimes on our computers, these things happen. Right? So that is one very important concept that I tried to put in a nutshell to give you an idea. Because in most of the cases, and pretty soon, I mean, probably in the very next slide, you will see. Okay, that's what we are going to study right here. See, everywhere, whenever in your book, on the internet, wherever you look at these operating system in a uh, visually conceptualized depiction, and this is OS, it's always in this way. So these are the application programs, these are the hardwares, and squeezed between them, the two of them, this is the OS, the operating system, the system programs. And the system programs has two parts. The operating systems, as you can see, that this is usually referred to as the kernel. And these are system programs. They are also running inside the system. That's why. But for all of them, there is a layer that is created, which is called user mode. So user mode is a buffer, is a play area, is an environment, you might say. User mode is an environment. In all the modern operating systems, they have created this environment to facilitate the seamless operation of most of the application software. Now, please take note of what I said. I said in all the modern operating systems. But when we started learning computer, when we were students in the high school, okay, in grade 12, when we were learning computer science the first time, we didn't even have Windows. We had to use I think some of you may know that OS. An OS called MS-DOS. It was a black and white interface, a black and white OS, not like Windows, not GUI based. It was not a GUI based or WIMP based interface. Essentially, what it was the kernel, only the kernel. That environment that we were talking about just now, that gives a wonderful playground to all these user apps to play around on top of OS, was missing. It wasn't there. So we just had the kernel of an OS, and in fact, uh, if you Google, you'll get to know that this is the very first operating system that Bill Gates he himself wrote these OS when he was just a student in Harvard, and then that was the beginning of Microsoft. So this was just the kernel, but it was working. It was working absolutely fine because most of these control and coordination related modules of codes are all embedded right here inside the kernel. So the kernel of the OS is the most important part. The codes inside the kernel, they have been organized in such ways so that each bunch of code or each module can actually take care of an interaction with a particular underlying software. One is responsible for the interactions with hard disk drive, one responsible for memory management, one responsible for managing input outputs, another one responsible for process management. So we have all these codes because try to understand this operating system and you just split it up into multiple parts. Think of each of them as a bunch of codes. Right? And each of them taking care of one particular interaction with one particular underlying hardware component. So maybe this is the one that is called file systems, taking care of hard disk drive. Another one taking care of the I/O operations. Right? So that is exactly how your operating system works. A very interesting thing right here, it's getting cluttered. Let me clear it up. A very interesting observation right here. Now, as I said, that in general, we say there's hardware and here's an operating system and the application programs. But now the hardware, most of the time, we mention that what we mean by hardware is the physical device, isn't it? Whenever I mention hardware, the first thing that will come to your mind is either a hard disk or a CPU or RAM, something that is tangible, something that you can touch, you can pick up and you put it in a pocket. Right, you can carry in your pocket. That's the hardware. That's the physical part of it, the physical device. But when you look deep inside your computer, we have to understand that for each physical device, we have to implement a certain microarchitecture. And this concept of microarchitecture is very important. I can tell you in most of the other chapters, I mean, the main chapters that we'll be studying later, you will find a very common word that we will use And that is the essence of how operating system works, literally. And that is mapping. You go to hard disk management, you go to RAM management, it's all mapping. Mapping, mapping, mapping. Now, what is this mapping? This mapping is, think about it. I will sometimes I will give you some simple analogies. I love to give these analogies just to clarify a complicated idea. So I mean, just think for a moment, stepping aside from these technical things, that what we have here is a plot of land. It's a plot of land. Okay? It's a plot of land. It's probably 100 square meter. 100 square meter plot of land. That is something that you can see. This is something physical. Now you are standing in front of it and you want to do something on the land. So what is the first thing that you will have to do? What is the very first thing that you will have to do? You have just seen a land in front of you, 100 square meter. What do you want to do? You want to do something. Now, it depends on your purpose, how you land. Try to understand. These are a little bit abstract concepts. But if you understand it, a lot of things will clear up automatically. What I mean, if in your mind you have a plan to do some kind of agricultural activities, growing crops on this 100 square meter land, then you will view it from that perspective. You say, all right, I will split it up like in this way. If you want to set up a garden on these 100 square meter plot, if that is what you have in your mind, then you will view it in a slightly different way. Then no, if I want to make a garden, then I will first decide where exactly I need a little bit of a pond. And then the flower part, the flower garden, and then a little bit of an orchard where we'll have some fruit trees, a vineyard. You will plot it in a different way. It is still that same 100 square meter empty plot of land. And then if in the other case you have something else in your mind, you say, no, I'd rather build a house on this 100 square meter area. Obviously, you will start plotting it in a different way. This is my bedroom. This will be my toilet. Here's my kitchen. Here's my balcony. You will reinterpret again and again the same plot of land in different ways. Why? Because you have different purpose and you have different plans. That is where this micro architecture comes into play. This micro architecture comes into play. You can change the micro architectures because depending on the micro architecture, the OS will start interacting with the actual physical device in certain ways. The interaction between OS and the underlying physical device depends on what kind of microarchitecture has been implemented on that physical device. That's it. Okay? And this is essential. For example, you have RAM. You have RAM on your desktop, and you have RAM on your cell phone. Both of them are the same physical device. They serve the same purpose. But I can assure you that the cell phone's RAM has a different kind of layout or microarchitecture that is implemented on it. So the Android, your OS, while interacting with that cell phone RAM, will do it in certain ways, which can't be done on your desktop in the similar way. So your Android OS can't run for the cell phone. I think Android also have a desktop version. Can't run straight away on your desktop. Same with Windows. You have the Windows for the desktop version. You have the Windows for the mobile version. So it all depends on that micro architecture. And as I mentioned this word, remember this word, mapping. We'll be finding this word everywhere. And it will over the time. If you get used to this word, if you get used to this concept, you will enjoy operating system. But if it's really hard for you to get to that point of that level of abstraction, then some of you may struggle. I can find it a little bit complicated too, but it is all about mapping. Okay. I will give you another one because we in hardware in the later part of this chapter, we will use a word, and I think some of you, if not all of you, you may have heard about that. Address space. This is something the very fundamental to memory management that we'll talk about. What is it? Mapping. So wait until we go at that point, and we will see that how mapping works. So my point here is to give you an understanding of what we mean by this microarchitecture. So these machine codes, the machine languages, are running right on the microarchitecture. And why these machine languages compatible with the microarchitecture? Because through these machine languages, the operating system is passing the control towards the device, trying to control interaction with the underlying actual physical device. Right. Moving on, a program that acts as an intermediary between the user, the computer, and the computer hardware. Very simple. An intermediary between a user of a computer. Now, a user, not necessarily you or me, but essentially, we are not supposed to interact directly with the operating system. We know it, right? So what we can do, we interact with an user software, user program. And at least we need an interface. For most of the OSs, there's at least one interface that they give for a direct interaction. And that interaction interface is what we call shell. Remember, in your labs, you have been asked to install Fedora shell, right? So shell is an interface. And if you use as an user, as an individual user, you can interact with the shell directly by writing some commands. Usually it's a command line interface, and it will go straight to the kernel of the operating system, and kernel will respond to your commands. But in general, you're not supposed to do that. An OS is not supposed to take direct command from a user. If you want to interact with OS, well, that's not our actual purpose, because that's not why we want to use computer. We want to use computer because we want to use some apps, and through those apps, we want to do something. We want to generate some output from the hardware, from the underlying hardware. It just happens that OS is right in there, in between these apps and hardware, to control and coordinate all the interactions. So that's it. So when you click a button on your Microsoft Word, say for example, you want to save a file, right? Save a file. So you clicked Save button on your Microsoft Word. And as you put it, the Microsoft Word gives a call to some of the codes inside the operating system's file system module. And this file system module in turn will now get in touch with the underlying hardware, that is the hard disk, to do whatever needs to be done to dump those byte blocks, right? Those byte blocks right there in the form of a file. I'm not going into details right here. Keep it simple. Okay, there's a whole a bunch of interesting things happening there. And we'll talk about it in that chapter. So it will go to the physical device, that is the hard disk, and it will write wherever it needs to be written. That's it. And then once the job is done, an acknowledgement will come back to the operating system's file system module. When file system knows the job has been done successfully, it will signal back to your Microsoft Word. This is Word, and Word will probably display a pop-up message that your file has been saved. Right. That's how it works. So we can clearly see exactly where we stand: the computer hardware, the operating systems, and the application programs. As I mentioned, in very early operating systems, this part was missing. When we were talking about MS-DOS, this was what we had: MS-DOS. Everything black and white. So essentially, you are interacting with a kernel. Even to this day, MS-DOS is still there, and we know it. It's running as Windows Shell or CMD prompt, command prompt. Whatever you can do by clicking on your desktop icons in the Windows environment, which is essentially the beautiful user mode, with beautifully visually enhanced, whatever you can do by clicking on any of those icons, I can do the same thing, and perhaps more than what you can do, by writing extensive commands on the command prompt, which is like kind of black and white, nothing visual there. If you type something incorrect, Then you'll have to retype it again because the command will not work. So that was the MS-DOS, which is basically the kernel and just a shell. Shell, as I say, is just a unique interface, usually command line interface, that is given for direct user interactions. That's it. All right. Moving on. We have two wonderful concepts here. OS is an extended machine. Well, you may think so. Because when we think about our interaction with computer, we are only more interested in app. Specific apps will give us specific desired solutions for problems, certain problems. And we only think of hardware because we can see it. We can see the hardware, we carry it in our backpack, okay? So we feel the pain. So that's why probably we remember the hardware. And the apps. We love the apps. What we forget about is the OS right here. That is where we call it an extended machine. Because these interactions, the app that receives the input and gives out the output, and hardware that eventually processes, this is the one where the processing is taking place. We are always interested in IPO, right? Input, process, output. So who is responsible for the processing of data? It is, at the end of the day, the hardware. Okay, so it is processing is happening at the hardware level, but the inputs are coming through apps, and the final output that has been generated will be displayed to us because we are right here, standing right here, to us through an interface on the app. So sometimes we forget about what is happening in between. There are lots of complex, complicated things happening. Most of these things are related to passing the control. Passing the control, as I mentioned before, and a little bit of coordination as well. Right? So this is exactly what is happening. And these complex things have been hidden most of the time. It hides the messy details of how the things are performed. That's why we call it an extended machine. On the other hand, we can also look at OS as a resource manager. This is where, so in this part, you can better say this part contributes to the word control, and this part is coordinate. There's a coordination. Each program gets some time with a resource. Each program gets some space on the resource. Just a minute. Get some water. That is exactly what is happening inside OS: control and coordinate. Now, as we say these two words, that each program gets time with the resource, and each program gets space on the resource. That's true. Because remember, in the first class, I was talking about, in a casual way, of how in modern computers, CPU, which is a resource, is switched from one process to another process. Sometimes a little bit on process one, and then it's taken back and is given to process two. So process two, process one, process three, process four, they're running in a pseudo parallel way because the CPU, which is one single resource, is being shared among them. So P1 will have its time and space on CPU, and after the time is over, then it will be the P2's turn, or process two's turn. So that is how it works as a resource manager. That brings us a little bit to the history of operating systems. Well, at this stage, if you have any question, you can ask me. As you're moving on to the history part related to concepts. All right, let's move on to the history part. Well, history is like always boring, but it's all about information and you have to remember. I think you already know about these things because you studied computer science, Introduction to Computer Science, CSI 104, and you know the history of computers. So this is where it all started. It's especially Turing machine. Remember von Neumann model. So this was all happening right in here. No OS. No OS. No needed. Not needed at all. Because these these were all plug boards. It's like circuit board. If you want to pass a command, one line of command, you have to have someone there to change the circuit, plug this switch here, switch this switch here, that switch here, and one line of command will be executed. So there's nothing called operating system. The operations were all based on simple circuits with some vacuum tubes to help uh, pass the current, the electronic signals. The second generation computer is where we started having the first operating systems called batch systems, which eventually, even to this day, we call it, you may have heard, mainframe computers. Mainframe computers. Okay, those were during that time, the next 10 years, the IBM mainframe computers. IBM was a lead there in the mainframe computers. They were all batch system. Now, what is a batch system? A batch system is quite different from multi-programming system. As you can see, in the next generation, we are looking at ICs, where ICs were introduced. So first, it was all vacuum tubes, were replaced with transistors, and were finally replaced by integrated circuits. Okay, now, uh, the batch system, as I was talking about, is quite different from the way it works, different the way that it works from the multi-programming computers. Because in multi-programming, as I mentioned just now, a CPU, so basically there are process one, process two, and process three, for example. They are at the same point of time loaded on RAM, and CPU is getting switched. Or in early multi-programming computers, CPU was not switched, but these these programs where these processes were constantly getting swapped in and swapped out. So remember, there are two words. We'll see them later. Switch and swap. They're not the same thing. Okay. When we go to memory management, I will explain in more details what's the difference. Very interesting. So basically, in modern computers, we switch the CPU. These processes are already there on RAM, and we are taking the CPU and switching them from this one to that one to this one. In the meantime, the second generation computers, when the first time we introduced the batch systems, that means that now you start a job and you can't interrupt it. So in other words, only one task at a time from start to finish. Not like multi-programming that CPU is doing a little bit of this one and then switch to the second one, a little bit of that one, and back to this one and back to that one. No. It was just like you start a job and it continues to perform the tasks in a logical and sequential way, and it terminates voluntarily. So those were the systems that we call batch systems. So we still have some mainframe systems today, and definitely the OS that we use for those mainframe systems must be different from the multi-programming OS that we use on our desktops. For example, your ATM machine is one of the most common thing. It is principally a mainframe computer. The OS that is inside your ATM machine works in a mainframe way. That means in a batch processing way. So it's systems because you try to remember that you try to think of your experience. Maybe some of you have this experience that you went to ATM to withdraw some money, and probably by mistake you pressed the wrong button. Well, there's no way you can cancel it or you can step back until you complete that transaction. In some older machines, not here, in some other countries I've seen, in some older machines, that so if, for example, you go there and you want to withdraw the money, so you punch your card, you insert your card, but by mistake, instead of clicking on the withdraw button, you click on balance inquiry button. And as you press on the balance inquiry button, a transaction starts. In some older computers, you had no choice. That you have to, whether you want it or not, you still have to go to the screen where the balance will be displayed to you, and then the card, your inserted card, will be spit out by the machine. Transaction over. Want to do another transaction? Reinsert your card and start it again. That is the nature of batch systems. Okay, we'll talk about it when we go to the zoo. Finally, the fourth generation computers, 80 onwards, we have our personal computers where we depend on switching. Okay, so that is how it is going at the moment. The history of the computers, some visuals, moving on. Okay, just a little bit of details. First generation, as I mentioned, no need of OS. Okay, machine language, and plug boards. Second generation, IBM, was all dominated by IBM. Mainframe computers. And the mainframe computers were all batch system. Please remember these words. Okay. Later, when I move on to, these are the new slides actually. When I move on to use my teaching slides, you will see that I have highlighted, I've tried my best to highlight some key words and key concepts to grab your attention. It's very important that you at least remember those key words. Batch system is one of them. You'll be finding this word everywhere. So if you're not familiar with this word, get used to it. The batch system. Batch system means a process is started and there's no way an operating system can interrupt that process during its operation. Once a process has been started, that particular process must continue until it voluntarily terminates. Okay, that is uh, the characteristic of batch systems. That's it. In fact, as you can see, you're using three different machines, and you need someone to take this one out, this one is processing, input tape, output tape, card reader, tape driver, then input tape, and put it, this is the actual machine, and then finally from there, output. And for this one, it was all the cards, card reader, and finally the printer. Now these card readers were basically punch cards, not smart cards. Have you seen punch cards? Just go to Google and type punch card. If you type punch card, you may have seen it. We used to see it in our school days a lot. Punch card. Okay, you don't see it these days, but because we don't use them anymore. But when we were using the mainframe computers, these punch cards, the stack of punch cards, it's a very common feature. So that is exactly how it used to work. And so thinking about operating system was right here. So part of it processing right here, part of it processing right here, and part of it right here. Fortran monitoring system. You don't have to worry about too much of details of these things. These are gone in the older times. In the third generation computer, it was still multi-programming. For the first time, the multi-programming was introduced, and the concept of time sharing was uh, introduced as well, but in a very different way. But this generation of computers lay the foundation for the next generation, the fourth generation of computers, that is PC. So what we had in those days were the two key things that I'm looking at is Unix. All of you know about, you may have heard about Unix. Unix, in our times, we had to learn Unix. Unix was all about sharing files in real time. An OS that was very, very, very popular in the industry. It was even before that there's Windows or Microsoft was born. Before Microsoft was born. And now you still have it, in the form of Linux. Linux was born on Unix. More than 80% to 90% of what you have inside Linux is fundamentally Unix. But Unix had a structure, had a unique interface, and it all it was uh, it was a real it gave us a real platform for real-time data sharing and multitasking. Then we also had Multics. Multics, triplexed, it was all about memory management, multiplexed information and computing service. Another big milestone that eventually, at this point, evolved into what we have today as the Intel Pentium. Pentium. Intel Pentium. So we have this Intel Pentium that micromanages the implementation of memory management following the same guidelines that were introduced in Multics. You can, and I will, if later I find some good videos in Multics and Unix. Unix, of course, you can learn easily, but Multics, that I will definitely share it and add it to my playlist. So these were the two hugely important things. But their structures were quite different. They were still not exactly switching the things. And even they were switching, they had their programs in dedicated place. As you can see, the job 2, job 3, job 1, and this is the operating system. And there were definitive memory partitions. Definitive memory partitions. Okay? The 3 jobs in memory as only 3 jobs at one time, and the partitions were definitive. Remember this word partition. When you use the word partition, what's the first thing that comes to your mind? It is something, as in English we say, hard and fast. Hard and fast means that something that can't be changed. For example, that is changed so easily. For example, we have partitions on our disks, on our hard disks, right? A partition is a partition. So when you have fragmented or partitioned your RAM in that way, in 3 or 4 chambers, just like we are doing on our hard disk, and you run one job in each of the partitions, well, you can call it multi-programming, but there were problems, inefficient usage of memory management, or in other words, it was creating a long time problem in memory management, that was fragmentation. Memory fragmentation. That was a problem that we were facing. But anyway, those were the early days of multi-programming, and that's how the things were being played out. It's the same thing that we are looking at right here. That was uniprogramming. You can see there's a wait part. Now, if you are interested in why do you have to wait, why do you have to wait? Well, there can be many reasons for why you have to wait. One of the reasons that you'll have to wait is to respond to I/O. Because remember, from the second generation computer, in fact, when we are talking about these early third generation computers, in terms of I/O, what did we have? A keyboard and a monitor. Sorry, there was no webcam, not even a mouse. Not even a mouse. A keyboard and a monitor. Monitor for display, and probably you can connect it to another port, the printer. That's it. And the keyboard was the only way that you could give an input. So this waiting period was to receive the inputs and generate the outputs and send the outputs to the display units like monitor. And this is the runtime. But when it comes to multi-programming, this is what is happening. Someone is waiting and the others are running. Okay. Multi-programming with 3 programs, just taking turn. Then came the 4th generation computer, and there we are. As you can see, this is the one that I was talking about, disk operating system, or DOS, which even to this day, all of us, we have it, the backbone of our Windows. If you just type CMD, you'll get the command prompt, and you know it very well, the things that you can do by clicking on the icons on your desktop environment, desktop Windows environment. I can do everything by writing appropriate commands on the command prompt. So it's still there. So that's what it looked like. Then we had the GUI and the Macintosh that came, and came Windows 3.x. I didn't use 3.x. 1985, I was still using MS-DOS, I still remember. And then, yes, my first Windows experience was with Windows 95, and that's it. I learned a little bit of Unix. We had to, because if you want to find a job in those days, in a company, in a good company that has some sort of a computer installed in their office, then learning Unix was a must. It was all about multi-programming and sharing over LAN. Yes. So this part is quite familiar to all of us, right? So that brings us to the next part: operating system zoo. Talking about zoo, we are just trying to tell you something about the diversity of operating systems that we have all around us. Because, as I mentioned on the first day, if someone asks you, where can I find an operating system? The answer is simple. Whenever, wherever you see an interactive electronic device, rest assured there must be an operating system somewhere deep inside it. It could be installed, maybe embedded, maybe already hardwired. In whichever form it comes, there must be something called operating system in it because it's an interactive electronic device. And that's what we are looking at right here in the zoo. We are looking at the zoo. So we have the mainframe operating systems. Check this word that I mentioned before. Then we had server operating systems, multiprocessor operating systems, personal computer operating systems, real-time operating systems, embedded operating systems, and smart card operating systems. We'll just touch upon these things in a very casual way, just to let you know what is what and introduce the keywords. That's the most important thing. Mainframe, batch, you know it. I just talked about mainframe computers, right? That's what we call the mainframe. That's the batch processing. And what is batch processing? Start it, let it go on and on and on until it terminates. No operating system will not interfere with the process to interrupt it or will try to switch it. In other words, at any point of time, only one process will be running. Okay, we have an example of that, OS by 390, and you can go to your ATM machines or maybe in the automobile industry. In the industry, inside the factory, we also use the mainframe computers. So in the morning, some engineers will come there and set up the circuit, switch it on, and that's it. The production will start half an hour later at the other end of the factory. Like at the end of the production line, you'll get the actual deliverable. Okay, everything neatly assembled and finely packed and delivered. So it is a process, a continuous process. So once the process has been started, you are not supposed to interrupt it. Server. The operating in the server operating system, the server operating system, server, as we understand, is something that is the server. The most important thing about the server, like I still remember that when I was a student, when I heard this word server, I asked my friend, what is a server? So he jokingly said, the server is something that serves. That's a server. Yes, that is what it is. Think about your servers. We have the web server, we have the database server, you'll be learning application server, you play your games from the game server, So everything is served. And they're serving to multiple clients. They're serving to the clients. So this concept of client on the one end, basically clients, one to many. And they're getting a service. They're sending a service request to the server, asking for something, and the server is responding to that. So the point here is again how one single computer, preferably with one single CPU, can serve. I'm hearing a noise here. Wait a minute. Wait. Where's the noise coming from? Where is it coming from? Anyway, so this is what we are talking about, the server operating system. Something special about the server operating system is this client, multiple clients, okay? And there can be multiple different kinds of servers in one single server. Now, for that, we have the same hardware. Of course, the hardware capacity will be much larger, much robust than a personal computer, which is not a server. But on top of that, there must be a certain microarchitecture. This is what the microarchitecture that must be implemented in such a way that we can engage most of these uh, hardware resources to serve multiple clients at the same point of time. So the structure of the OS, this goes to the structure. We'll talk about it in the structure part, is where we prefer to implement microkernel. What is microkernel? Microkernel literally means that most of the non-essential jobs have been taken out from the kernel. Most of the non-essential jobs have been taken out from the kernel. So if those jobs have been taken out, those responsibilities have been taken out from the kernel, then naturally kernel will be quite free. Okay, now the most of the non-essential tasks will be taken out from the kernel. And that will be a critical thing. So that if you keep your kernel as light as possible, your server will be more responsive. You will understand why it is important later, because whenever the operating system is running, as I said just now, that it is constantly switching back and forth from user mode to kernel mode. Now, when it is working in the kernel mode, it actually slows down a little bit, because that's exactly where most of the control related actions are taking place. User mode is just an environment to play around. It runs everything that runs from that layer, from that level, is much faster than anything that is running from the kernel level. So if we can keep this kernel part very small, micro, minimum, that means you make the entire machine super fast. And this is, I tell you, this is one of the strategies that was implemented by Apple. That's why Apple devices are super fast. And it's possible for Apple because Apple gives you both hardware and software. It comes in a package. Unlike your Samsung phones, that the Samsung gives you the core hardware. Of course, they have some software, but the main software, the operating system, is coming from Google, Android. So that is one of the reasons. And this is this technique, this structure, having a microkernel and taking out the non-essential parts and just keeping the important parts right in there to make the machine lightweight, make the kernel lightweight, and thereby increasing the speed. That is something that we implement for server operating systems. Okay. One more, multiprocessor operating system, high availability. In multiprocessor, it's all about sharing the computer bus, sharing the clock, sharing everything. Because there are multiple processors, of course, high speed, no question about that. Personal computer, the one that we are familiar with, we still have the same thing, interface to single user, the many OS, Windows, Mac, Solaris, and Linux, and many I/O devices. Real time, real time is all about. There are two kinds of real times. These real times, the hard real times, are mostly related to military hardware like missiles, rockets, and even in space technology, in aviation technology. So that means you fire a missile from here to hit a target, precise target, like 5,000 kilometers away, and there must be a deadline for every action and absolute precision. There shouldn't be zeros, there shouldn't be any margin of error. So we can't just say that after launching it, that, well, halfway into the flight, my missile hanged, my operating system hanged. No, it doesn't work like that. So these are the examples, and for the soft ones, something that is quite popular here, flying drones, for example. In real time, you see what your drone sees as it keeps flying over a landscape. Okay, so that is how we naturally for this kind of operating systems, real-time operating systems, there are two criteria. One is strict deadline, and literally zero error. That means precision. Absolute precision, zero error, strict deadline. You have to finish it within deadline. You can't delay it. Because if you get delayed, there will be a catastrophic situation. We do have a couple of others, but I will take a break here. And okay, just one other thing. When we come back again on Friday, please, at least one of you, I would ask you the first question is where to get started, and just remind me. Okay, you can take note on your book that we will continue to talk about this operating system zoo, and then from there we'll move on to the next part that is most likely computer hardware review. All right. Plenty of time, no rush. I will take your attendance. Where is it? There we are. Xuan Huang,
Yes.
Chi Kang,
Yes.
Vin Phuc, Juk Huang,
I'm here.
Luang Ha,
Yes.
Hu Huang,
Yes.
Tan Hum,
Yes, sir.
Nopfat,
Yes.
Linh Min,
Yes. Yes.
Quoc Huy,
Yes.
Quay An,
Yes.
Kim Thắc,
Yes.
Nhật Minh,
Yes.
Hiền Phúc,
Yes.
Quang Huy, Quang Huy,
Yes.
Minh
Yes.
Quang, Minh Quang,
Yes.
Duy Bao,
Yes.
Huay Minh, Liêm Trúc,
Yes.
and Quoc Hum.
Yes.
Okay, one person absent. Vinh Phúc. All right, thank you. That's all. All right. I don't want to drag it to the end. We'll move slowly forward. Give it a read. You have already downloaded the book. It's time just to read it like a storybook. Nothing more than that. Okay, just read it as a storybook. You have just listened to a part of the lecture. Open the book, the ebook, and give it a read. That's all. All right, so we'll catch up with you again on Friday. And probably on Friday, I will open the lab. I mean, the labs are open, but I'm going to set a deadline. Okay, by Friday. So officially, your labs will be open. All right, that's all.